Hello, everybody. It is week 4, and we have just decided at the beginning of recording the midterm date. And midterm date is going to be 3rd of March, and you will take the midterm exam during the same hours of lecture. So please update your agenda that 3rd of March, starting at 3 p.m., we are going to have the midterm. And we just decided on this. Okay, note it, please. Okay, this is the first thing we should discuss. And the second thing is that I should also give you some problem assignments and the problem solving assignments. You are going to have 4 problem solving assignments until the end of the semester. And the first assignment will be related to pipe flow. Actually, I was planning to give it on the week before, but I couldn't prepare it. So you may expect that you are going to have your first assignment in this week. I mean, until Friday, I am going to assign you your first problem solving assignment, and I will send you an email. You will find it on Moodle. You will solve the problem, and typically I give around 5 days or maximum 1 week to solve such problems, and then you will upload on Moodle. That's all. Okay, it is a problem solving assignment 1. And you may expect to get it in this week. No certain time is given now, but I am probably going to upload it as soon as possible after the tutorial tomorrow. Anyway, I'm going to just make a kind of recovery in the tutorial. By the way, thank you, Takmina. She reminded me, and also you did a very good job in terms of voting and asking for other students. It is great. I like it very much. So I know that there is a certain amount of students they have a desire to have a kind of tutorial, kind of recovery. Maybe you are going to ask me questions. Even I will prepare 1 or maybe more questions with solution for tomorrow. And you will have a kind of tutorial session tomorrow. Okay, noted that it is not going to be a teaching and it will not be recorded, okay? Instead of teaching and recording, what we will do, we will have just a kind of, free discussions. You can ask me any questions if you had difficulties in solving the problems. So before coming to the tutorial, I strongly suggest you to make a kind of review. And if you do not understand anything, you can ask me. Still, it is possible to solve 1 problem to update, okay, or maybe more. So I am going to work on it, and I will prepare some extra problems maybe, and I will solve them. And don't forget that I am not going to record it. It means that if you miss the tutorial, you will miss it, okay? It is only for the students attending the tutorial. And tutorial time is 3 o'clock tomorrow. If there will be a cancellation or something, I am going to send you an email. So you may assume that we are going to have a tutorial tomorrow. Okay, is there anything you like to ask today before
Yes.
Okay, Russell, please.
About offline lab session, is there any updates?
No, offline. Most probably, as I told you, we are going to have the offline lab sessions after the spring break, if you will be in the campus. I don't know, did you receive any call from the university to come back to campus? Guys, could you please update?
Several students, yes, they said that you can apply for the dormitory, but several other students who are educating in other school, they already started
offline.
Yes.
So most of our students are in the campus, right? So okay, most probably we will conduct those lab sessions after the spring break. This is the plan, actually, the original plan, and we are still with this plan. And also, I like to say that if you miss or if you couldn't find a chance to join the offline sessions by any problems like having a COVID or other issues, I think we can also keep a camera, okay, active and just on during the during the lab activity. Most probably, if a student has a kind of reliable, acceptable excuse, you can still follow it online in a synchronized way. But again, we had an agreement with the head of department. I had an agreement with the head of department, and again, I am repeating that most probably the lab sessions will be offline. It means it will be in person in the lab, okay? So we are going to do it group by group. So just wait for us to organize the groups, and we will invite you accordingly. Okay. So it is at the moment it is not set when and how we are going to do it.
Thank you.
Okay, I thank you. Any other questions, please, if you have?
The link for tutorial session tomorrow is the same as for the lecture.
What do you mean? Is the same? Yeah, the link. I am sorry, I couldn't hear it. There was a problem in this sound delivery. Yes, the same link you can use. Okay, so that link is a permanent link for the hydraulic course. So that link will be used. I mean, you can use that link for any time to join my courses and tutorials. You are right. The same link, please. Use the same link. Okay, guys, let's go. Okay, so I don't know what do you see on your screen. Do you see my presentation, full screen presentation?
Yes.
Yes.
Okay, great. Okay, guys. Now, as I told you, in week 3 we finished pipeline flow, and today we are going to start making discussions and learning open channel flow. And open channel flow is a kind of one of the main topics in hydraulics. So actually, this could be a little bit new for you because some concepts are a little bit different than pipe flow. So that's why I strongly suggest you to follow me carefully, and please ask me if you have any questions and any hesitations while you are listening. Just drop in, step in, and ask your questions. I will be very happy to respond. Okay, let's start. Okay, when we say open channel flow, it means a kind of flow. It is not a kind of pipe flow. Actually, open pipes can be also considered as open channels. I will explain you how. Be patient. So open channel flow refers to the flow in liquids in channels if their surfaces are open to atmosphere. It means that actually it is not necessary for it to open atmosphere. Think in that way. If there is a flow and the surface of flow is not touching anything, okay, if it doesn't touch any surface, and if atmospheric pressure on the flow is 0 because of the free surface flow, it is open flow, okay, open channel flow. And I want you to have a look at this pipeline, for example. If in this pipeline, if flow is not full, like half of pipe is full, and you have a flow like half pipe, maybe less than half pipe or maybe more than half pipe, but the surface of the flow is not touching to the surface of the pipe, it is still open channel flow, okay? So typically in open channel flows, I think you just realize that it is not a pressurized system like pipe flow. So it means that you are not pushing the water by pressure. Rather than pushing by pressure, the water is flowing itself by the effect of gravity. So open channel flow is always on the direction from higher elevation to lower elevation, okay? This is the concept of open channel flow. Is clear, guys? So please note it that these are two important concepts in open channel flow. The first one is the atmospheric pressure on this flow is always 0. I mean, equal to atmospheric pressure. We don't have pressure. It is not pressurized system. And because of having no pressure, the second important thing is that that flow is always from higher elevation to the lower elevation. It means that it is a gravity forced flow, not pressure forced flow. Okay? So in real life, okay, I'm not talking about engineering structures. I am talking about rivers, flows in creeks, floods, or streamlines for run of water after the rain events. All those flows are open channel flows. They always find themselves, I mean, water is always find itself a channel, okay, and it flows in the channel. This is called open channel flow in the nature. All the river flow or any flow, water flow in the nature is the open channel flow. We have also engineering systems. Actually, we are interested in that part and the engineering systems. Irrigation systems are mostly open channel flow. Okay. I also have seen that several pressurized irrigation systems, but this is the conventional way. I don't know, have you ever seen any irrigation system in some part of Kazakhstan, maybe your town or hometown or other places? most probably you have your experience with those channels, okay? And sometimes they are structured like canals, okay? Even we are using canal and channel, both terminology. I mean, it is not a kind of different pronunciation. Canal is different, channel is different. So you can have some irrigation canals or channels, and also you can have some sewer lines, and almost all the sewer lines in the world, okay, sewage systems, I mean, these are open channel flows. Even though we are delivering, conveying, or let's say we are delivering the sewage system water, sewage water with the pipeline system, but the pipeline is not a kind of pipe flow. It is channel flow. It means that water in a sewage system is not fully, it's not fully flow. It's not filling the pipe fully. And there is always a kind of empty space on the top, and it flows like a kind of channel flow. And also drainage ditches and gutters are the other examples of engineered systems. They are typical open channel systems. Saying something, Sabrina? Sabirjan? Pardon, sorry, Sabirjan? No? Anybody say something? No. Okay, by the way, can you, if you don't hear me, just let me know. There is a kind of instability in the internet connection nowadays. So that's why I'm asking you, are you hearing me? Is it okay? Just, it will be good if you provide some feedbacks. Okay, let's continue. And flow characteristics are also important, and you should understand. Actually, you are quite familiar with those terminologies like steady flow, uniform flow, but now you are going to learn two more terminology: rapidly varied flow, okay, and gradually varied flow. These are two new terminology we are using to define type of flows which are different than pipeline flow in open channel flow, okay? So steady flow is the same like pipe flow. If there is no change with time at a given location in velocity and flow rate, it is called steady flow. So think in that way, I'm just focusing on one particular location of the one particular location of the channel, open channel. And if the volume, it means flow rate and the velocity is not changing at that particular time during the period of your analysis, you may say that, okay, this flow is steady. Uniform flow is something else. Uniform flow means that, assume that you have a kind of channel like 100 meters long, or let's say 1 kilometer long. And uniform flow is, the flow should be the same characteristics at the beginning and at the end of the channel, okay? It means that the flow is not changing through the flow system by location. This is called uniform flow. And rapidly varied flow is, actually rapidly varied means that it is very fast flow. In a very short distance, the flow is very sharp, very fast, like waterfalls, okay? And you may assume that it is happening in waterfalls. And gradually varied flow is a kind of flow, and the changes, like changes in the uniform flow or steady flow, is happening over a long distance, even if it's very difficult to recognize it by eyes, okay? So because of the friction, anyway, there is not a kind of, in real life, there is no uniform flow in a long distance. I mean, when the distance increases, because of the friction, there will be differences in the flow from the beginning and end. But by assumption, as a kind of to solve the problems in engineering approach, in practice, we assume that the flow is uniform. You may say that, okay, in the channel, the height of the flow is around, like, for example, 25 centimeters, and the shape of the channel is the same in everywhere. And after 1 kilometer, you may assume that it is going to be at the same height, like 25 centimeters. But in real life, this is not going to happen. You are going to lose some height, okay, because of the friction. It's energy losses. But while we are making some calculations, we first assume that flow is uniform. We are solving the problem. Then we are calculating the energy losses. I will explain you later in the coming weeks, coming days, how we will do. So we are designing the system by assuming that the design system is uniform. Guys, noted that. We are designing the system that the system is uniform, but later we are calculating the energy losses, okay? So this is a trick in open channel flow. It is a kind of significant different way than what we do in pipeline flow. flow, okay? Because in pipeline flow, you cannot do that. In pipeline flow, because of the continuity of mass, if the pipe size is the same in everywhere, the flow will be always the same. I mean, the velocity will be same, flow rate will be same. Whatever you lose as energy, you are going to lose pressure, okay? Not from velocity. You are going to lose your energy from the pressure, not from the velocity. But in open channel flow, it is not. In open channel flow, even you may lose some velocity, not only pressure, even you may lose some height or let's say depth in water level. And one more thing, as you know that there is no slip condition in every flow. It also the same for pipeline flow and open channel flow. But in practice, we assume that the flow is the same in everywhere and it's average velocity. So we are using only one velocity value for any given place in the pipeline and in the channel. So it is the average velocity. This is our assumption. Okay, these are some details about the characteristics. I think everything is clear. Do you have any questions, guys? Okay, maybe you like to have a look at this picture. Sorry, this is the cross section or y-axis, and you see that the flow, we have a kind of pipe open channel flow, and in this part of the channel we have uniform flow. UF means uniform flow, and then when it gets closer to the waterfall, okay, a kind of elevation difference, it starts speeding up, and after a certain level, water starts speeding up and the velocity increases dramatically, and then it turns into that region gradually varied flow. It means that the flow is gradually changing. Have a look at that. Even you can observe that there's a kind of difference in the height of the flow in a short distance. Okay, and after that we are going to have a rapid flow, very fast flow, and then we are going to have a kind of hydraulic jump here. After having a hydraulic jump means that our flow is going to lose energy, and then it starts again flowing slowly. But before reaching a uniform flow, you are going to have a kind of gradual varied flow before the uniform flow. So this is a kind of typical structure of a kind of energy dissipation system, which is constructed for, delivering water delivery systems in most of the places. And I know also I was in Almaty. I think you were there as a Kazakh person, most probably. You will see that there are such systems available. I mean, such a kind of engineered structures or in almost all the river basins. This river basin is a kind of structure for energy dissipation. It means that you are dissipating the energy of the system. You are just absorbing some energy of the system, and you are slowing down the flow of the water. If you don't have a kind of structure, if you have a kind of straight water basin, a channel, the flow is going to be very fast, very rapid, and it's going to be dangerous for everything. I mean, and it's also going to be dangerous for the city, and it's also not a kind of controllable water flow. It may create some flood events and other problems. That's why the engineers, water engineers prefers to make such structures to dissipate the energy of the system. And by this way, the water flow will be slowed down significantly, and you are going to have a kind of controllable flow. This is a kind of flow controlling system in river basin. Okay, I think it is clear. Okay, let's continue. Do you have any questions, guys?
No.
No? Okay, good. Sabirjan, yes. Sabirjan. Okay, let's have a look what kind of equations you are going to use. And you remember that how to calculate hydraulic radius. Hydraulic radius is the same. It is equal to wetted area over wetted perimeter. But just be careful that if you are making a calculation for wetted perimeter, you are not going to add the top of the water because it is free surface. It doesn't touch anywhere. So, for example, if you have kind of rectangular surface, you are going to add the length of sides and bottom. That's all. You are not going to add the top. So I think you just realize that hydraulic radius for open channel flows are larger than hydraulic radius for pipeline flow. Okay, because of the lower perimeter value. The area is the same, but the perimeter is smaller in open channel flow. Actually, it is good. It means less friction. And the surface of the water is not having a friction effect. It is not losing energy because it is open channel. It doesn't touch anywhere, but air is not, has no friction effect. And hydraulic diameter is another thing you should remember. In the earlier lecture, I mean, in previous week, I just mentioned to that, be careful. Hydraulic diameter is not half of the hydraulic radius. Sorry, hydraulic radius is not half of the hydraulic diameter. Hydraulic diameter is just 4 times of hydraulic radius. Okay, so there's an explanation here in red box. So it might be a little bit unusual for you, but this is hydraulics, and in hydraulics, this is what we do. And noted that hydraulic diameter, okay, hydraulic diameter is 4 times of hydraulic radius. Or just the opposite, hydraulic radius is 1 over 4, I mean a quarter of hydraulic diameter. Okay, and Reynolds numbers, you can calculate the Reynolds number in the same way, but if you like to use radius, then you should convert, I mean, you should replace the diameter value with 4R, I mean, for hydraulic radius value. It is the same equation. And I want you to look at, I mean, please take your attention on the right, see that we have different criteria for turbulent flow and laminar flow. For laminar flow, the Reynolds number is supposed to be less than 500. As you may remember, it was 2,300 in open channel flow, but so it was 2,300 for pipeline flow, but for open channel flow, it is 500. And it was 400 for pipeline flow, but in open channel flow, it is 2,500. So this is the criteria for the Reynolds number. So if you are comparing or if you are analyzing if the flow is turbulent or not, please refer the correct numbers as given on the screen. And one more thing, you guys, in real life, flow is almost always turbulent. Okay, so most probably you will not be able to see any laminar flow in real life. But there are some ways. For example, if you like to see a kind of open channel laminar flow, you can make an experiment at home. So, for example, take a flat plate, I mean like dinner plate, and just rotate it and put it under your tap water and open the tap water slowly, just just aim for the middle of the back of the plate. And then you will see that tap water, allow it to flow slowly, that water will just disperse around the plate. And just at a few centimeters, you will see that it is going to disperse or it is going to spread on the plate very smoothly, okay, without no waves. And it is a turbulent laminar flow you can observe in real life. And the laminar flow is not going to stay for a long time. I mean, it's just a few centimeters. You will experience it. And when it starts fluctuating, like making waves on the water surface, it means that it is not laminar anymore. Any wave on the surface, it means flow is turbulent. Okay? So in real life, almost 100%, all open channel flow types are turbulent flow. So we are going to focus on turbulent flow only in the hydraulics too. And let's go for the left bottom of the screen, and it is here an example calculation for you for the hydraulic radius. As I told you that, let's assume that this is a kind of rectangular channel, and the height of the channel is H and width is B, and water depth is equal Y. So here the area is going to be Y times B. Okay. And of course, the height of the channel is going to be a little bit higher than water depth. Water level should be lower than channel. Otherwise, water is going to go, it will go spill out. That's why high is just a kind of design criteria. And we are going to calculate the required amount of Y. Then you are going to add it a kind of 10 or 15 centimeters on the top of it. Then you are going to have a kind of structural design of the channel. So H value is going to be a little bit higher always than Y value. And this is how you are going to calculate. Have a look at that. What we have y time b, it is area, and b plus 2y is the weighted parameter, and this is the resulting equation of the hydraulic radius. Okay, let me check my timing. Okay, we have already left. Past half an hour. Okay, guys, do we have any question on the screen? Anyone would like to ask anything? Okay, it's good.
I have a question. So in the real life, is there so there's almost no occurrences of laminar flow like in the nature?
Yeah, no. You can observe it for a second. I mean, just at the beginning of some flow, as I gave you the example. Okay, if you take a kind of plate, reverse it, and put it under a tap water, then you see that just the beginning of the flow, when it disperses over the plate, there is no fluctuation, there is no wave. It is laminar flow, but it is not going to stay long. After a couple of centimeters, it turns into laminar flow again. So this is very exceptional case. If you like to have a kind of laminar flow in the real life, the flow height is going to be a couple of millimeters only. Okay, and when the height is increasing, you are not going to have laminar flow. So this is a kind of approach, or this is a kind of general rule. You may assume that almost always the natural type of flows in nature, and even in engineering systems, are turbulent, linear. Okay. Okay, let's continue with the next. Okay, so what I told you, just noted that while we are designing, we assume that flow is uniform. Okay, flow is uniform, and if the flow is uniform, these are the equations. You should know that. We are going to use Kolberg equation, we are going to use Darcy-Weisbach equation, we are going to use Moody chart. They are exactly the same charts and the equations we can use. And also you can use Chezy equation, okay? You should remember that I introduced you what is Chezy equation in the earlier week. So here the Chezy equation is given, and please note that C value is also a kind of functional value of F, friction factor. And this F friction factor also comes from the Kolberg equation, okay? And F is also, you remember that this is the equation for F. It is exactly the same equation, invented by Kolberg. So in order to calculate F value, you can use this equation by using the hydraulic radius and roughness value. Then even you can calculate the C value for Chezy equation. Then you can estimate the flow rate and the velocity of the flow by using the equation of Chezy. It is suggested here. And here S0 means, okay, S0 means the slope. The slope is hydraulic loss over length. Okay, slope is easy to calculate, it's hydraulic loss over length. And most of time in engineering systems, it is defined for you. For example, in order to have a kind of smooth flow, as it is described here, okay, have a look at here. This is a kind of typical flow you are aiming for. Like you want a kind of velocity higher than 0.5 meter per second, but most of time in open channel flows, you don't want a kind of velocity more than 2 meters per second, okay, because it is very fast flow over 2 meters per second. So you like to have a kind of flow between 0.5 and 2. Typically, as I am a kind of experienced engineer, and while I'm making a kind of open channel flow design, I am typically starting with 1 meter per second, okay, velocity. So this is my default value. I am selecting it to make any iterations or any calculations. And typically an open channel is going to have a kind of hydraulic radius larger than 0.1 meter. And again, typically the Reynolds number is going to be a kind of fully turbulent flow, like more than 50,000. And these are the values. And most of the time, again, we are using this dynamic viscosity, kinematic viscosity value, and we are referring that water is flowing at 20 centigrade degree. But in some exceptional cases, if you are living in a cold climate environment and most of the time the water is keeping a kind of value lower than this value, then you can use another value. But most of the time in measured part of the world, this is a kind of typical reference value for our calculations. And this is how you will make a kind of estimation of the velocity Guys, again, I am repeating that. Listen me carefully how you are going to solve a problem. In the design, as you are engineering, the hydraulic loss, the low hydraulic loss will be given for you. For example, they are going to say that you are allowed to have 5 meter energy loss, okay, hydraulic loss in one kilometer flow, okay. It means that you can easily calculate S0. How you can calculate S0? 5 meter over 1,000 meter is going to give you S0 value, okay. So it is here, and then most probably you will not be able to know that what kind of diameter, I mean, what kind of structure we have. And then you are going to decide on the structural parameters. Later we will discuss how you are going to decide on the value of B and Y, okay? So because there is a kind of best hydraulic design concept. Next time on Thursday, I am going to explain you what is the best hydraulic design concept. And most of the time while we are making a design, we are just selecting those best design parameters to minimize loss and maximize the performance and velocity and flow. And then you are going to optimize the structure. Then you will decide that what is your structure, and you will identify, you will calculate your hydraulic radius. And if it is unknown, you are going to keep it as an unknown, and then you will make iterations to find between the energy loss and between energy loss and the velocity value until reaching the correct velocity value. You will make iterations and you will solve, and you will decide the right design parameters for the best open channel dimensions. Don't worry, we will solve problems and you are going to get it, how to solve. And let's make a kind of simple problem, solve a simple problem. And I think it is going to be our first problem in this open channel flow applications. I'm not pretty sure. I think the lecture is going to be over after this one. Yes, this is my plan for today. And I will solve you this problem and then the lecture will be over. Let's solve it. And then the lecture will go over. Okay, let's have a look at that, what we have. We have very smooth cement plastered surface which forms an open channel, and you see that it is a rectangular channel, and the height of the water is actually Y value, not height of the channel. The height, depth of the water is 0.5 meter, and the bottom of the channel is 0.6 meter. Okay, and your aim is to carry 0.25 cubic meter per second. I mean, in this channel, you are aiming to carry like 250 liters per second flow. It is most probably used for irrigation or other activities. And this is the target for these are the design criteria. And the design is not allowing you to have a depth more than 0.5 meters. So in this case, in order to carry or convey that amount of water with that kind of material, I mean the channel material, what should be your F, C, and S0 values? Okay, so this is the question we are trying to answer. Okay, let's have a look. Look at the solution, and then I think everything will be clear for you. Okay, the first thing is first, in such calculations, in such problems, first you should calculate the hydraulic radius. And hydraulic radius is easy to calculate because we know all the parameters here. We know the height, we know the depth. And this is an easy question, guys, because it would be also possible that in such questions, you will not be given the dimensions, okay? So in this case, you have to design it yourself and you have to select, I mean, if the dimensions are not given, there are two options. One option is that, the question can ask you, use the best design parameters. It is easy if it is best design parameters because we know that how to make a selection based on best design parameters. I'm going to introduce you later on Thursday. But even though, even the alternative is that maybe it is not also given. In this case, you are supposed to make a kind of selection by yourself, or you are going to find the correct solution by making a kind of iterations. It is going to be a kind of difficult type of questions if it is not given. Okay, let's continue. And the dimensions are given for the channel, so it's quite easy to calculate the radius, hydraulic radius, and you see that it is 0.5 times 0.6 over the parameter value, and it is around 0.19 meters. Okay, around 19. Yes, 19. Yeah, it is around 19 millimeters. Okay, And the Reynolds number, let's calculate the Reynolds number by using the equation and the values given here. And the Reynolds number is pretty high. Definitely it's a fully turbulent flow. And if it is turbulent flow, you can use Colebrook equation. And again, I am repeating that there is no way that you can get a kind of flow laminar in open channel flows. And most of the time you are, I mean, all the time, let's say, you are going to have laminar flow. But anyway, it is good to make a kind of cross check if it is laminar. Okay, who knows what's going to happen? Check it out and be sure that it's laminar flow. Sorry, turbulent flow. And this is our F value you can calculate. We know the hydraulic radius and we know the epsilon value. It is given in the question. And the rest is very easy. Then you can calculate F value as 0.016. So this is the F value for that type of flow and that type of material. Okay, that type of channel. And how you can calculate the C value? Again, in the earlier part, I gave you that how you can calculate the C value. C value is a function of F value. It's quite easy, very simple equation. And then you can calculate the C value as 70. And if you put C as 0 and hydraulic radius in the equation of Chesney, then you will be able to also calculate the hydraulic slope. Okay, you will be able to calculate the hydraulic slope. It is actually a hydraulic slope or the slope of the channel. It is given as this. Okay, so this is the value, and it is telling us that okay, this is in okay. There is no unit here. There is no unit here, and if you assume that, you may assume that it is around 76 centimeter energy loss per kilometer of open channel. Okay, so this number is telling us that there are 3 zeros here. 76 centimeters. Yeah, 76 centimeters of energy loss. It is less than 1 meter per kilometer of pipeline, per kilometer of open channel. Okay, there is no unit for S0, there is no unit for F, there is no unit for C. These are just constants. And S0 is not a constant, it is a value, but you are calculating, you are calculating by dividing energy loss in meters to length. It is in meters, and there is no unit in the resulting value. Okay, guys, it is the end of the lecture for today. And if you don't have any question, I like to stop now.
Yes, thank you.
Okay, if you have no questions, we can stop now. Okay, see you on Thursday. Oh, no, not Thursday, tomorrow at 3 o'clock for tutorial. So be ready, okay? You should have your questions. If you don't have questions, I'm not going to answer you anything. Maybe if I am kind enough, I will find some problems for you and I will solve it, okay? A kind of extra support, okay? But in tutorials, we are supposed to make a kind of discussions in the classroom based on your questions, okay? This is actually the way how we are conducting the tutorials. But in this time, maybe I can solve a problem. I am going to find a problem for you today, and I will solve it tomorrow, most probably. Okay, guys, see you.
Thank you. Bye.
Bye-bye.
Thank you. Goodbye.
Goodbye.
Thank you.
Thank you.
Goodbye.
Bye-bye.